Jordan. Hello, Aliyah.
Hello.
So I'll be teaching from home this week.
Okay.
Yeah, one of the students got COVID, so I think, I have not been contacted by the health department, but it is good to stay home.
Oh, okay. One of the students in the department, I'm guessing.
Yeah.
Gotcha.
So, but I think I interacted long back, but so it doesn't seem like it should affect, but still, it's a good idea.
Yeah.
Stay away.
Take any precautions you can, because I can tell you what, it's not fun for some people.
Yeah.
Like myself, I haven't actually got it yet or anything, and hopefully, hopefully I got it and had it without any symptoms. That's the hope.
Yeah.
Then I won't. And I haven't seen you without a mask in a while. I'm used to you looking like a ninja up front.
Fun. Yeah, that's correct. Yeah, every lecture I have to wear a mask. Correct. Yeah. Yeah. How is the audio, by the way? I'm not using the mic. I remember last semester, you guys preferred me using a mic.
It's good. I think it sounds good.
This is okay. How about when I'm turning back? Is this okay still?
Yep, it's good.
Okay, that's good. So I don't have to use the mic then. Okay. Aliyah, how is everything at your end? Hello, Luke.
Hi. This is your home setup?
Yes, this is my home setup. So I was just telling Jordan that one of us in the department has been diagnosed with COVID sometime back, but the test came out only yesterday. So I think it is good to stay home for some time, just as a precautionary measure. So that's it. Okay, so I think let's. I gotta zoom in, I suppose. So it's a homework 10. It's due December 3. It should be. I think I have that are only 2 questions in it. You should be able to do most of them from whatever we cover today, and rest of it will be in the exam. So let's. And the final exam has been posted. Complete exam has been posted, and it is due on December 8th, I suppose. That's Tuesday at 10 a.m. What else on exam? Yeah, that's all, I suppose. Is there anything else I should be mentioning about exam? It's available on D2L right now. I think that's all. And like in the earlier course, there's a course evaluation available. I will encourage you guys to take that. This is available on D2L. Okay. Is that readable? Okay. So since we have changed the setup, so feel free to mention if I'm not doing the right thing. Yeah. Okay. Let's go back to the So we started on spherical harmonics. So today let's define the spherical harmonics basically as much as we can. The hope is that I can actually define them today, and on Thursday I can actually use it in a slightly different context, probably in the quantum mechanical context where you build it out of harmonic oscillator operators. So today here, I will simply be introducing it. Remember what we said? Let's think of a construction A dotted with R. Right, that's a position vector, and A is a constant vector. And let's raise it to a number L, a whole number L. And let's see under what circumstances does this satisfy the Laplacian. Laplacian operator is the gradient operator squared. So there are two gradient operators. The first one, let's operate it with the first one. We did this already. So let's say this is L times A dotted with, let me actually rewrite this onto the right side. It doesn't matter. So this is L times A dotted with R raised to L minus 1, right? That's how you will differentiate this quantity as a whole. But then you have to use the chain rule. I have to differentiate everything inside. And for that purpose, I write that in the opposite order. So that's R dotted with A. And then you recognize that, oh, that's just the operator 1. So this is operator 1, or the unit dyadic. And that gives you just a vector A. So let me write that again. So sort of repetition. So that's A vector A times L times A dotted with R raised to L minus 1. This is a constant vector. It doesn't depend on the position, so I can move it out of the gradient. So this becomes A dotted with, so this is a directional gradient if you want. And L also can come out. And I have A dotted with R raised to L minus 1. That's pretty much the same operation that we just completed just now. Again, it will give you an A. This time instead of L, it will bring out an L minus 1, and we will get an L minus 2 there. So this will yield L times L minus 1 times the dot product of these two vectors, which is A squared times A dotted with R raised to L minus 2. And we're going to ask the question, under under what conditions is this going to satisfy the Laplacian? Right? We have already, our goal here is that we found out that there are some class of solutions like dipole moment or the electric monopole moment, quadrupole moment. They all satisfy the Laplacian except at the point, at the position of the point source. And we would like to classify them. And here we notice that for any arbitrary order L, this will be satisfied if the right-hand side was 0. But right-hand side can be 0 in various ways. I can set L equal to 0. If L equal to 0, the whole thing is 1. So that's a trivial solution, right? Laplacian of 1 is 0, of course. Even for L minus 1, it is trivial because then it is linear. The gradient operator has 2 operators, so at least you need to have two variables there, like x square, right? At least x square, so that it can contribute. So that's also not straightforward, or it's trivial if this is 0. If this A dot R is 0, again, this whole thing goes to 0. That's not good. So the only solution that is possible is that A square is equal to 0. So if we want this to be a solution, then a requirement is that A dotted with A is equal to 0. So, and then we ask what kind of vectors, what kind of vector has that property? If you have a vector A, which is A1 I hat plus A2 j hat plus A3 k hat, square A dotted with A equal to 0 means that A1 square plus A2 square plus A3 square has to be equal to 0. And we realize that if they're real numbers, so the square of 3 real numbers will never be equal to 0. That's not a possibility. So the only possibility is that these are all complex. So if A1 and A2, A1, A2, A3 are complex numbers, then since this is a complex equation, then there are 2 constraints there, right? So, so there is a A1 square plus A2 square plus A3 square is some x plus IY, where x and y are real. So that, and that's equal to 0. That means there are 2 constraints, right? So this implies that x is equal to 0 and y is equal to 0. So there are 3 complex numbers which consists of 6 real variables. So 6 real variables plus 2 constraints, right? Plus 2 constraints. That means there are 4 real variables available. That means we can fit it as 2 complex numbers. Right? So the point is A1, A2, A3 seems to be too much of information here. So let's replace this with 2 complex numbers. That's 2 complex numbers. With that motivation, let's define these 2 complex numbers. So let's say A1 plus A2. Notice this is still complex. A1 is a complex number.
I think you
and A2 is a complex number. Of course, A1 plus A2 will also be a complex number. So this we will define as.
I think you'll need to zoom out just a little bit.
Oh, I am in the wrong area. I forgot. Thank you. Okay, good.
Yes.
Thank you. Yeah, for those who came a little late, so I'm teaching from home today. One of us was diagnosed with COVID, so it turns. I mean, I think everything is okay, but I think, and I was not contacted by the health department either. But I thought I should stay home, so just so that everything is okay. Okay, so so this is a setup at home. Some of you have seen it in the last semester. So it's okay. So we're doing spherical harmonics. We want to build it out of a vector. So this is called a null vector, right? So A is a null vector. So, and we argue that there are 3 complex numbers, but then there are 2 constraints. So you need only 2 complex numbers. And we will use we will call these 2 complex numbers y plus and y minus. As of now, it is just 2 complex numbers as it sits there. But later, if possible, I'll do on Thursday. What I'll do is that I'll show that this represents 2 harmonic oscillators, like y plus and y minus. These are 2 operators acting on harmonic oscillators in quantum mechanics. But for now, we don't need that information at all. This is just 2 complex numbers, and let's say this is y minus squared. Okay, so it's a complex number, but it's a square of that. And the second is a1 minus ia2, and that's equal to minus y plus squared. So 2 complex numbers, y plus and y minus, and that's how you define them. And the claim is that now I've specified 2 of them, so the third should be determined by the constraint, correct? So third complex number, A3, A3, let's say, right? A3 square is equal to minus A1 square minus A2 square. And so this is A3, right? So square of that, right? Square root of that. The complex numbers of square roots are well defined. That's equal to what is A1 plus A2 square? A1 plus A2 square is nothing but A1 plus IA2 times A1 minus IA2. So that's a simple way of seeing it. Even though these are complex numbers, when I multiply them, A1 square, and since it is the cross terms will cancel out, and I get A1 square plus A2 square, right? So A1 times A2 and A2 times A1. So that's the same as, so this will be equal to minus of A1 plus IA2 is y minus square. And this is y plus square, but that's it comes with a negative sign, so that makes it a y plus. And the square root of that is simply y minus y plus, or it doesn't matter, so there is no order in here, right? So y minus y plus. The complex numbers, so unlike quantum mechanics, these are completely commuting with respect to each other. So we know how to write A3 in terms of y plus y minus. We would like to write A1 and A2 also in terms of that. So let's write A1 and A2. So A1 would be equal to, add these 2 equations, then A2 cancel out. So that's y minus square minus y plus square divided by 2. And A2, similarly, is I have to subtract them, correct? And then there is a 2 times I. So this is y minus square plus y plus square divided by 2 times I. Right, that's your equation. That's your variables. What is your vector A1 in terms of A1, A2? So let me write the vector A itself is, instead of writing ijk's, let me write that as A1, A2, A3. And that's equal to A1, we said that is, suppose I take out a factor of 1 by 2 overall out. A1 is y minus square minus y plus square. A2 is, there is a factor of I there. So I had to, let me move it upstairs. So that's minus I. And A3 is 2 times y minus y plus or y plus y minus, doesn't matter. Okay, that's your vector A in terms of these two complex numbers, y plus and y minus, correct? That's what we have shown. So again, what have we done? We said that there is a quantity A dotted with R raised to L. That's a solution of the Laplacian if there exists a null vector A whose square is 0. And that null vector we built out of two complex numbers. That's all, right? And using this, we will define what is called the spherical harmonics. So, okay. Any questions as of now? Okay. So we have to define, or let's, again, let me write this down. So there exists a vector A, a null vector A can be written in terms of two complex numbers. And this is minus I. And 2 times y plus y minus. And we also have the vector R hat, let's say, or let me write R, vector R, and then divide it out. So as a magnitude of the vector R, its x component is in spherical coordinates. It is sine theta, cosine phi, sine theta, sine phi, and cosine theta. So, so in terms of this, so there are these variables theta and phi. So notice this depends on angle theta and angle phi. And of course there is R, but we will divide that out by R. And here there are two complex numbers, y plus and y minus. So anything I build out of this will depend on these four quantities. So in terms of this, we are going to define, right, A dotted with vector R. It's R hat, but I'll divide it out by R instead of writing it R hat, right? A dotted with R divided by R, that's A dotted with R hat, and raised to L, right? That's what we said would satisfy Laplacian. And we have one, and just for normalization, I will divide it by L factorial also, where L is a positive integer. Now we are going to, if I since this has these features, if I had to multiply these two quantities, so this will depend on those 4 variables, right? And those 4 variables, I'm going to expand this as, so this is our definition. L, it is possible to expand this as M going from minus L to plus L, and Y plus raised to L plus M divided by L plus M factorial. Remember your other functions we have defined. We have a generating function. We write it as a series, and the coefficients are identified as some functions. So that's L minus M divided by L minus M factorial, and there's a square root. And if you recognize, these are exactly the harmonic oscillator operators. Actually, they come exactly with the same coefficients, L plus M factorial with the square root. There's also a 4 pi divided by 2L plus 1. And does it have a square root? Let me check. I'm not sure. Yes, it has a square root. So this whole thing is inside a square root. And now notice this is a series in terms of y plus and y minus. But this doesn't have to be that. So whatever are the coefficients, that's what is defined to be the spherical harmonics. But that has to depend on theta and phi, because we built it out of 4 variables. 2 of them we expanded it out, and whatever is remaining is defined as the spherical harmonics. So YLM phi are spherical harmonics. But we haven't given you, I didn't give you what spherical harmonics, what exactly YLM is. And that's our goal today. We are going to find out what exactly YLM is. And that will be done. How will we do this? We are going to use this A, multiply it with R. So we get the left-hand side, expand that out, and expand it out exactly in this form, and identify the coefficients, and we will read the spherical harmonics out. So that's how we are going to define. So that's going to be our strategy here. Again, multiply these two, so we get the left-hand side, expand it out, and write exactly in this form, and whatever are the coefficients, we will recognize or read out spherical harmonics in that sense. Is the strategy clear? Any questions there? Okay.
Why does this expression not depend on R?
Oh, because I divide it out, right? So the position R divided by R, right? R hat. So that is how I'm defining.
Okay, I see.
Right, this is R hat, correct? So if you want, you can write this. So that's, I like to write it like that. So this is R hat.
Okay, I see. Thank you.
Right, so it doesn't depend on the position R. That is one small feature in here that you can ask. I earlier motivated that A dotted with R is the solution of a Laplacian, but now I'm talking about divided it by R. And there you can show that if A dotted with R raised to L is a solution, anything divided by R raised to L will also be a solution. So that part I'm skipping. So that's just a long proof there. So that is a small logical, if you think in the motivation sense, there is a small logical gap in there. But I don't need it because I'm just defining it I'm just going to use this expression to define my spherical harmonics. So maybe that's what bothered you. Okay, okay, so that's our goal. So begin with the left-hand side, right? Let's start. Let's find A dotted with R hat. So A dotted with R hat. And I will raise it to L also, but first let's begin by A dotted with R hat. So I simply multiply the X components out there and Y components out there and Z components, right? So it is surely 1 by 2 is there. So the 1 by 2 times Y minus square minus Y plus square times sine theta cosine phi plus not plus, right? So it's a minus I over 2 Y minus square plus Y plus square times sine theta sine phi. And let me try to put this, squeeze it in here. That's plus 2 and 2 cancel out, so that's I keep, so that's 1 by 2 times 2 Y plus Y minus and then cosine theta. Okay. Hopefully that's readable there. Okay, is that readable? Yeah. Okay.
Oh, never mind.
No, it's not.
I didn't see you pulled the I out. It's I over 2. I didn't see that.
Yes, it's I over 2. Yeah. Okay. Okay, so this is equal to 1 by 2. Let me keep the 1 by 2 all the way out. And let me collect the Y minus out first. Or let's say Y plus. Yeah, Y plus, Y minus. Yeah, Y minus first. So that's Y minus squared. That has a coefficient of sine theta common. And then there is cosine phi. So I've taken care of this. And this is minus I sine phi. Same thing with Y plus. That's minus Y plus square. Again, sine theta. Cosine phi. This time, since I've factored out the minus, it is plus I sine phi. And finally, since I've taken out the 2, so this is plus 2 Y plus Y minus cosine theta. Good. Clearly, this is exponential of minus I phi. And this is exponential of plus I phi. So what we have here is, if I were to write the left-hand side there. Oh, I should be moving this, I suppose. Yeah, still the visible region. So that's 1 over L factorial times again, I go back to, it's A dotted with R hat, no doubt about that. But, being in your homework, it's sort of like this. So let me put you guys into this. So I raised to L here. So this is equal to, so this whole quantity has to be raised to L. So there's a factor of 2 that gets raised to L. So that's a 1 over 2 raised to L. And then there is L factorial. And this whole quantity raised to L. So that's Y minus square sine theta e raised to minus I phi And then there is minus y plus square sine theta e raised to plus I phi and plus 2y plus. Pretty much copying copying the earlier line back. We want to expand this as a series. So basically, we want to binomially expand this. There are how many terms? Like if there is a plus b the whole square, there are 3 terms. A plus b the whole cube, there are 4 terms, and so on. So we want to expand this in that form. Before that, we want to process this a little. So let's take the y plus quantity out. So I'm taking the appropriate one so that this will be useful for processing later. So I keep this 1 over 2 raised to L factorial, and then I pull out a y plus square out. So that's this quantity. I also pull out the I raised to exponential of e raised to I phi. And I pull out an extra sine theta, not from the numerator, but from the denominator. It's a trick. And since the whole thing is raised to L, I have to raise this to power L. So this whole thing has been taken, factored out. So I have to provide that back in all the terms that doesn't have that. So in the first term, I need y minus square over y plus square. I pulled out a sine theta from here, so I have to provide a cosine theta in there. Right? So I took out a sine theta, so this becomes sine square theta. I pulled out an e raised to I phi, so I had to put in an e raised to 2 I phi. So that's what comes in the first term. In the second term, this is simply sine square theta. So that's what remains in there. And finally, in the second term, so this is all, the goal is to, this will all help with the binomial expansion that we will see soon. Plus has been taken out, so I had to divide it out, right? So this is 2 times y minus over y plus. I pulled out a sine theta, so provide that in. I pulled out an exponential of plus I phi, so that's minus I phi. And finally, there is a cosine theta still remaining. Notice this can be thought of as a square of a quantity, and this is those 2 squares showing up. So there is some feature in there. Expand this sine square theta as 1 minus cosine square theta, so that you get this cosine theta out. And then you notice that this whole thing can be written as 1 over sine theta whole raised to L. And I want to write this as a square. So this quantity here, cosine square quantity, that becomes a plus, remember. And the last term together, that's a whole square, which can be written as y minus over y plus sine theta exponential of minus I5 and plus cosine theta. Plus, correct? Plus cosine theta. And just a square. And there is still a -1 remaining raised to L. That's what we have achieved. So just a processing point, and the y, because we want to expand this in this form and expand and collect the spherical harmonics out. Okay. Pretty much algebra there. But now notice this whole quantity can be thought of as, let's say, this is your x. Let's say this is your x. Let me call this whole thing a raised to squared -1 raised to L. So this has that construction in there. And let me define this to be I L x plus a. Okay. So what I'm going to do now is that I'm going to process this and bring it back. So we have basically used some notations there for this big expression. Process this as a sum and then bring it back and substitute it in here. Okay, so that's going to be our strategy. Any questions? Again, we expanded this in terms of y plus and y minus. Our goal is to identify the coefficient in front of this y plus, y minus. So we are expanding this. So that is something raised to L, but we want to be a little careful with that expansion. So how to expand that, that's all. Okay, so we have we reduced our problem into expanding this in terms of in a binomial expansion, right? So this is x plus a whole square -1 raised to L. How do we binomially do a binomial expansion of that? Of course, we can expand this as a simple binomial expansion. Then there are double binomial expansion, right? But we can use a small trick. This is a translation operator, right? Remember that exponential of a times d by dx of f of x is equal to what? Anyone? Is that a familiar? Probably did this in E&M maybe? No? So let's expand it out, right? So if that's not familiar, so this is a d by, that's a derivative operator on an exponential operator, not very familiar, but it's just Taylor expansion actually. Right? So this is expand. Whenever we have a exponential operator, it's defined as a series in one way of looking at it. Every function has a series representation. So this is nothing but 1 plus a d by dx plus 1 over 2 factorial of a d by dx squared, right? And so on. Acting on f of x. Right? So that's That's how you will look at it. And then you will see that, oh, that's nothing but f of x plus this is a times derivative of f with respect to x plus 1 over, so this is a square over 2 factorial times second derivative of f with respect to x, and so on. And what is that equal to using Taylor expansion? What's that equal to?
Zero.
0. Why do you say that? No? Why did you say 0?
I don't know.
Or maybe you're seeing something, yeah. Think of Taylor expansion. So what is that? So what's the series equal to, right? I know sometimes, usually Taylor expansion, how would you do Taylor expansion?
Well, it would be f of x plus f of a, right? Is that
F of x plus a. Good, good. Right. So this is f of x plus a. Right? Or did you say f of x plus f of a?
well? That's what I said, but yeah. f of
It's
x.
actually f of x plus a. Is that reasonable? I think I don't know whether it was in this class or not. We had some discussion on this, how you guys see this as a Taylor expansion, and we had some, there was a small question raised as to is this correct or not, and then we had shown that explicitly. Okay, is that good? Okay, but the simple thing is, oh, this is nothing but this, correct? Or you can say that's a series, right? So same thing in here. You can remember this series in this form. So that's equal to, if you want, let me write it on the right hand side so that I get some space. That's a d by dx of x squared minus 1 raised to L. That makes, otherwise you have to expand this in L and then again break that binomial, right? So it just gets rid of that double sum in a sense. But exponential, I know, this can also be written as, right, sum n is equal to 0 to infinity 1 over n factorial, and then there is a d by dx raised to n, right? And of course, you apply it on the force, the function f. So in that sense, this is nothing but n equal to 0 to infinity. That is 1 over n factorial. And we have this n operators, n derivatives, if nth derivative if you want, acting on x squared minus 1 raised to L. X squared minus 1 raised to L, does that ring a bell somewhere? That particular construction in any of the special functions that you saw? Right. Legendary polynomials has that construction. So Rodriguez formula, I think, but that's okay. If that's not there, but so we're sort of seeing the structure in there. Okay, so. But this is surely probably not completely necessary to do this form. Notice that this is a something raised to L. So if it's in a positive integer, when you have a plus b the whole square, you have 3 terms, a plus b the whole cube. There are 4 terms, and so on. So there should have finite number of terms here, but this goes all the way to infinity, correct? So that's probably not necessary. And it is easy to see that because this is a polynomial rate of rank 2L, right? So polynomial raised to 2L. So after, when n is 2L, that stops, correct? After that, the derivative is not going to go, right? So it's not necessary to go all the way. So I don't have to write n goes all the way to infinity. Instead, I have to go n equal to 0 to 2. Right. So this piece is not necessary because this is an nth derivative of, if the polynomial doesn't have sufficient number of variables, it will eventually go to 0. So that restricts the sum from 0 to 2L, and that clearly shows that there are 2L plus 1 terms in there. Remember, we were looking for, so we already argued that a spherical harmonics will have 2L plus 1 degrees of freedom, right? That was the motivation we made in the last class. So that shows that that's the 2L plus 1 terms. But typically, we don't like to write it in terms of n. We often go from minus L to plus L. So let's define, or let's substitute n is equal to L minus m. So instead of going from 0 to 2L, we'll go from minus L to plus L. So that means m is equal to L minus n. So that's the substitution I'm making. So I want to rewrite in terms of m instead of n. So if I do that, so m goes from, when n is equal to 0, m is plus L, right? Because n is equal to 0. When n is equal to 2L, m is equal to minus L. So I'm going from plus L to minus L. So it seems like I'm going in the backward direction. 1 over n is nothing but 1 over L minus m factorial. Then there is a raised to n. So let me write that right here itself. So that's a raised to n, which becomes a raised to L minus m. Right. And that is a derivative operator, d by dx. How many of them? Nth derivative, now it is L minus mth derivative. And x squared minus 1 raised to L. Okay. That's fine. This sum seems like it is going from plus L to minus L in an opposite sense, but it doesn't matter. Addition is whether I add 1 plus 2 plus 3 plus 4 or 4 plus 3 plus 2 plus 1, it's the same number that you're going to get. So just change the order of addition and nothing is going to change. So this is the same as, it's exactly the same as m going from minus L to plus L. So that's a raised to L minus m, L minus m factorial, and d by dx. In this form, we have all the ingredients we need to process our expression. Remember what we had arrived at. I'll rewrite that here because that's on the other board. It's L factorial a dotted with vector r over r. That's equal to, we said this was 1 over 2 raised to L, L factorial y plus square e raised to I phi let me write it slightly differently. So this cosine theta plus y minus over y plus square minus 1 raised to L. If you compare these two quantities, x is nothing but cosine theta. So I want to recognize this as x and this whole term as a. and that is a whole raised to L. So I can replace this as a sum now, right? Put this all together in here. Remember, if I expand this in y plus y minus, whatever sits in front is my spherical harmonics. So this is equal to, I put that sum in here. So I'll move this 2 raised to L factorial through the sum, write it later. So this is y plus square e raised to I5 sine theta raised to L, and then sum goes from m going from minus L to plus L. A raised to L minus m, A is nothing but this quantity in here. So this is y minus over y plus sine theta e raised to minus I5 raised to L minus m. Then I have to divide it out by L minus m factorial. Derivative with respect to x, but x is cosine theta. So this time I'm not supposed to take a derivative with respect to x, but derivative with respect to cosine theta as a whole. You can think of it as a chain rule. So the cosine theta is a variable. And that's raised to L minus m. And then we have cosine square theta instead of x, minus 1 raised to L. And remember that there was a 2 raised to L and L factorial. It's good to write it underneath that because that identifies the structure of the legendary polynomials. That's good, except that we want to process this as y plus and y minus. We want to write it exactly in a form so that we can identify our y plus y minus. So put this all in into the sum. So this is equal to m going from minus L to plus L. We have y plus raised to L, and that is a y plus raised to, so I have y plus raised to 2 times L, that's coming from here. And then there is minus L plus m. Right, that's coming from there. And that's it. What about y minus? That is y minus, there's only here, so that's L minus m. It comes with a factor of L minus m factorial. I'll write it underneath that itself right away. So I've taken care of y plus and y minus. What about sine theta? Let me see e raised to I5 first. So exponential of I5 raised to, that is L. And these are coming with minus L plus m, right? So it's minus L plus m, because that's exponential of minus of y. That is sine theta. I'm going to write it in the denominator. So that's sine theta in the denominator. That is an L, and there is a minus L plus m. So I've taken care of sine theta also. What else is remaining? And then finally, my derivatives. So that's d by d cosine theta raised to L minus m cosine squared theta minus 1 raised to L over 2 raised to L. pretty much very close to what we have, what we defined to be the series for the spherical harmonics, except in that definition, this was having a square root. Here there was an L plus M factorial, and there was this 4 pi raised to 4 pi over 2L plus 1 in there. So I'm going to process that much again in here. So the final step probably. This is M going from minus L to plus L. This is Y plus raised to L plus M. I divide this by L plus M factorial. This is not there, but I've added this in. So plus M factorial. This is Y minus L minus M already exists. But now I move out a square root, right? This is not having a square root, so I introduce a square root, so there is an extra piece in there. So that's L plus M factorial over L minus M factorial. Actually, yeah, so this is L plus M factorial square root. And finally, this is simply e raised to I M phi and sine theta raised to M, because L's cancel out. Sine squared theta minus 1 raised to L over 2 raised to L factorial. If I compare this with what we had earlier, I
was kind of thinking that maybe the sine theta should be raised to the negative M.
all right, is it? Let's see. Because it's in the denominator notice. So sine theta raised to L in the denominator.
Yeah, so that's negative. Would that be sine to the
Raised to L, right?
Yeah,
So that's sine theta, that's the first L.
yeah,
And this one is in the numerator.
right.
To carry it to the denominator, I have to make it minus L and a plus M.
Okay,
Because this is in the numerator. So I'm moving it to the denominator.
that makes sense. Yeah.
Right. Yeah. Yeah, it is slightly, yeah, because usually we are used to, this power is sitting in the top, but it's actually in the denominator.
Yeah, no, I was just thinking you'd have sine of L minus M over sine of L, and the L's would cancel, but that was silly thinking.
Yeah, but I think that's because I think one was seeing it that way, right? Okay, so this gives us theta y LM immediately, except that 4 pi over 2L plus 1 is not there, so you have to add and subtract. So everything from this point on, right? Everything from this point on actually is your spherical harmonics, except we have to put a factor of 2L plus 1 over 4 pi. 2L plus 1 over 4 pi with the square root, and L plus M factorial. Everything inside a square root, and that is an exponential of I M phi That's your spherical harmonics. As it sits, that's just an expression, but these are important functions. These are like Fourier expansions. If you have a function defined on the surface of your Earth, like if there is any function that depends on theta and phi, you can expand it in terms of L and M. Right? There are, for each L, M goes from minus L to plus L. right? So you can expand this in these functions. So let's see what are some of the basic small ones. Let's see L equal to 0, what happens, L equal to 1, what happens, and so on. So just see what these expressions are just for practice. And then, so we have about 10 minutes. Let's calculate some of the basic ones and go and see what they are. Any questions? Again, the motivation here is that any function that's a function of the angle theta and phi, which describes a quantity on the surface of a sphere, we can expand that in terms of spherical harmonics. And in that sense, it's an extremely important function. Okay, so the smallest is L equal to 0, right? If L is equal to 0, M has to go from minus L to plus L, M has to be 0. Right? There is only one function there. For L equal to 0, that's a unique one function. So that's Y 0, 0. What is Y 0, 0? L is equal to 0, so it's 1 over 4 pi. That's the first term. That is L is equal to 0, M is equal to 0, so it is 0 factorial over 0 factorial. M is 0, so there's nothing there, I suppose. That's it, right? Nothing. So Y 0, 0 is just 1 over square root of 1 over square root of 4 pi. Okay. If L was equal to 1, then M could be minus 1, 0, or plus 1. Right? So that's 3 possibilities. So let's begin with Y 1, 0. Here, y. So that's equal to, when L is equal to 1, so that's 3 over 4 pi. L is 1 and M is 0, so that's 1 factorial by 1 factorial by 1 factorial, that's 1. So, but M is 0, so still the exponential and sign doesn't contribute. And this is d by d. Let me write this as d by dx raised to L is 1 and M is 0, so that's d by dx. And then there is x squared minus 1 raised to again 1 divided by 2 raised to 1 and 1 factorial. But at the end, I have to set x equal to cosine theta. So if I'm writing x, at the end, I have to set x equal to cosine theta. This is easy. Derivative of first derivative of x squared minus 1 is 2 times x, correct? 2 times x, the factor of 2 cancels out. So it's just x. So this is 3 by 4 pi times x is cosine theta. Okay. Let's do y1 comma 1. Let's do y11, right? So y11 theta phi. Again, this will be 3 over 4 pi. Now L is 1, M is 1, so that's 2 factorial divided by 0 factorial. That's 2 factorial over 0 factorial. M is 1 now, so exponential of I phi over sine theta. And again, this time there are no derivatives, right? L and M is 1, so d by dx raised to 0 actually, and x squared minus 1 raised to 1 divided by 2 raised to 1 and 1 factorial. And our set x is equal to cosine theta. This gives me a cosine square theta minus 1, but that's just sine square theta. Right? And there is a denominator that is a sine theta. So there's a cancellation in there. And there is a minus sign also that's coming up. Right, so this is equal to minus sign because I'm going to flip 1 minus x squared. So it's minus of 3 over 4 pi. There's a factor of 2 also, right? So 3 times 2 is 6, and that is a factor of 2 in the denominator. So 6 divided by 16 pi. So that's 3 over 8 pi. It's 3 over 8 pi in the square root, and that is exponential of I phi and sine theta exponential. So, let me know if I'm making a mistake. I don't know the answer for this. You should be able to look up. These are so standard functions, you should be able to immediately get this. In your homework, I asked you to plot this. Right? These are nice functions. If you look up in Wikipedia, these are, and you need to plot it as a 3D graphics. Right, so I give you the command line. What is the program that you need to do? Also, use your favorite program if you use one. But if you don't use any, then I suggest you have to use something. But you have to pay for using Mathematica, so that's why I don't recommend everyone to do that. So use some software that that can plot 3D graphics, because these are 2 variables, right? There's a theta and a phi. So x-axis is used for 1 variable, y for 1. So z is for the 3rd one. So you have to use that. You can use angular plots also. Those are nicer. So I give you some commands to do that. Okay.
For anyone who doesn't know, there's a free version of Mathematica on the Wolfram Cloud.
Perfect.
So yeah, that's a useful tool.
Okay. Contact Moses. Yeah, get. Yes, a very useful tool. Yeah. So it is completely free. Is that what it is on the cloud?
Yeah, that's my understanding. I mean, you just have to have a Wolfram account, but yeah, I log in and
I've never used it. Probably I should log in once so that I know what are the features available out there, so that I can tell this is what is available. Okay, good. Yeah. Let's quickly do y1 minus 1 also. Yeah, y. And by the way, these are actually if you're done hydrogen atom, these are how your p states look like. So this is your s state. Angular dependence of the s state, not the radial dependence. Radial dependence is the angular dependence of the s state. This is the p state has 3, has a degeneracy of 3, right? 3 times 2, 6, because each state can have 2 electrons. So this is m equal to 0, m equal to minus 1, and plus 1. So those are your 3 states. Here, I expect this will be again 3 over 4 pi. But the next one, L plus M, that is 0 factorial, but in the denominator, this will be 2 factorial, I guess. And this is e raised to minus I phi. But now this is sine theta raised to minus 1, so it goes in the numerator. Sine theta raised to minus 1. Derivative d by dx of L is 1, M is, so this is squared. It's 2. And we have x squared minus 1 over, this remains the same, 2 and 1 factor. That is an x squared. By the time I take 2 derivatives, all the x's is gone. 2 times x and then x. So that's a factor of 2 and 2 cancel out. So that stays the same, I suppose, right? 2 and that cancels out, I guess. Why is it giving me a 16? So this is x equal to cosine theta. I would expect this to be exactly similar. So that is a sine square. No, there is no sine square theta, sine theta in the numerator. Huh. So this seems to be off by a sign. Or so this gives me, if I am seeing this, 16 pi, which is not correct. Sine theta e raised to minus I pi. I think these two, minus m and plus m, should be exactly the same. What am I missing? Help you.
I think the second one is giving you 8.
8? Oh, because
Yeah, I'm not getting
the square
16.
root. Yeah, yeah. So I don't have to take it. I thought this was, yeah, good. Okay, nice. So you see some symmetry there. Thank you for pointing that out. I was struggling. But these two are pretty much the same except for this minus 1 sign there, right? So there's a general feature in there which connects this YL of minus m will be minus 1 raised to m times YLM, which you will see in your homework, how we can see that. So that's a general feature in there. If you know this, you can immediately write down this. I explicitly did it, but this is always related to the other. So that gives you an idea. And this is also related to dipole moment. Remember, your dipole moment has this cosine theta term in there. Right? So let me stop here. And next time, hopefully I can motivate this in another context. Either I will do orthogonality of spherical harmonics, or I can show what are the differential equations that satisfy the spherical harmonics, or I will show this in the context of a harmonic oscillator in quantum mechanics. So I'll pick one of the topics and do that. And then we will finish that. Again, the homework and the exams are already out. You can start working on them. So next Tuesday, the course formally ends, right? So we will have the last lecture on Thursday. Okay. Good.
Okay, thank you.
Thank you.
Thank you. Yeah.
Thank you.
Bye.
Bye.
See ya.
Bye, Moses.
Bye-bye.
Was this any better than the classroom? Jordan keeps saying that he likes this better.
Oh, yeah, I think it maybe was a little bit slightly bigger font, like
Yeah.
I see.
yeah, I didn't struggle quite as much to read what you were writing. Yeah.
Yeah, I really enjoyed it. It was a lot, to me, it was a lot clearer.
Oh, okay. So a lot clearer. So that's a significant statement.
Yes.
So otherwise, it's you have to stress to read things from the board, is it? Okay. Okay.
Yeah.
Yeah, occasionally. It's usually fine since you're talking as you're writing. We know what you're writing.
Yeah. Okay.
Yeah, that's always a big help.
Okay. Okay. Good. Maybe I should zoom in there also. That's mainly here I zoom in. That's the main feature.
Mm-hmm.
So, okay, good feedback. Okay, enjoy, guys. Yeah, thanks.
Thank you. See you guys later.
All right, see ya.
Yeah, goodbye.